And do you have the Gaussian Law?
Hello and welcome back to another Pore Lab lecture series. Our today's speaker is Dr. Steffen Berg, Principal Science Expert at Shell Global Solutions. Dr. Berg is an experimental researcher with an interdisciplinary background in soft condensed matter physics, physics and chemical interfaces, and fluid mechanics. His current research interest is the Pore scale physics of multiphase flow in porous media. Today he is going to talk about upscaling multiphase flow from Pore to Darcy Scale. Thank you so much, Dr. Berg, for accepting our invitation, and here you are.
Well, thanks a lot for inviting me, actually, and it's a pleasure to talk today in your seminar. And the title of my presentation is The Upscaling of Multiphase Flow from Pore to Darcy Scale, from a geometric state function of capillarity to a generalized description of wetting. So before I forget it, I want to mention my co-authors, who are Ryan Armstrong and James McClure. A lot of the work has been done in close collaboration over a longer period of years. There's a lot more people involved, which I will acknowledge in the end. Another key person that is worth mentioning is Steffen Schlüter at the Umweltforschungszentrum in Halle in Germany. So just a brief background. The context of this presentation is multiphase flow in porous media, which is a situation that is encountered in a variety of applications and problem fields. In the geosciences, we have transport in the vadose zone, CO2 sequestration, and lately also like hydrogen storage. Then there's hydrocarbon recovery, which is a much more common topic, but also contaminant hydrology, where organic contaminants, some of which can be more dense than water, have reached somewhere the subsurface, and the remediation of these is subject to multiphase flow as well. More lately, we have come to the awareness that also in technologies like fuel cells, but also electrolysis devices, there is multiphase flow in the gas diffusion layers. And this multiphase flow can be a rate limiting factor for these devices. So also these communities are lately very interested in the aspects of multiphase flow. In particular, things like energy dissipation and so on might be a topic that is quite relevant. And not to forget, in everyday building materials, we have multiphase flow in sandstone rock in our houses, which leads to dry out and salt crystallization, which leads to damage in buildings. And that's a nightmare for a lot of historic buildings and respective restoration aspects. So and I don't really want to spend too much time on this because you probably know this already. We describe flow in porous media usually on the Darcy scale using Darcys Law, which is strictly speaking only a law for single phase flow. And you can derive it from upscaling Stokes flow by homogenization from the Pore to the Darcy scale. But for multiphase flow, the most commonly used approach, which is this two-phase Darcy equations, they are a phenomenological extension of Darcys law to multiphase flow. This is a much more pragmatic approach. There's not really a strict fundamental basis to this. And as a consequence, there are parameters in that formulation, like the relative permeability saturation function and also the difference of the phase pressures, which we need to obtain from a measurement. So these relative permeability saturation functions are typically measured in experiments. And the phase pressure difference is approximated by the capillary pressure, which is also seen as a function of saturation only. And there are all sorts of issues around that. For instance, these functions are typically hysteretic, and they also likely depend on more parameters. And that is what I'm going to talk about today. Strictly speaking, if you wanted to do this properly, you would have to describe the transition from Pore to Darcy scale in a more rigorous way. So when we look at the multi-length scale aspect, of the problem. We start at the top in hydrocarbon recovery. We have reservoir engineering models for hydrocarbon fields. And these are discretized in grid blocks that reflect the different geological structures. And each grid block is still the size of tens of meters. And in each grid block, we describe transport using that two-phase Darcy equation. And I put here law in parentheses because for two-phase flow, it's strictly speaking not really a law. But when we really, it's a continuum mechanics description. There are no pores, there is only porosity and permeability and saturation. So when we zoom further in, we see the individual pores in the rock, which are partially occupied by fluids, which are immiscible. And there is a very dedicated fluid distribution. And the evolution of this fluid distribution can be described by Navier-Stokes equations, because now we have still continuum hydrodynamics, but discrete pores. And inside of these discrete pores, we apply simply the laws of continuum hydrodynamics, which is the Navier-Stokes equation for each fluid phase. And then there is a coupling of stress at the interface, which is then implemented in the equation. And in this way, we can actually model that phenomenon. If we zoom further in, at some point, we reach the sub-pore scale and even the molecular scale, where phenomena such as interfacial tension, but also wetting are described. And that's more like down to the nanometer and angstrom scale. And the really insane, ridiculous, difficult part is that aspects from that nanometer scale are actually matter. They do actually matter for the scale up to like the kilometer scale at the reservoir scale. So that is really the difficulty, and it makes it very difficult to really address this problem. I'm focusing on here on the step from the Pore to the Darcy scale, where the physical concept changes. So this is more like for people who come more from a geological aspect. For them, upscaling means usually heterogeneity, but here we change the physical concept, and that's the challenge. So we made tremendous progress since about 10 years by imaging the displacements at the pore scale directly in 3D rock at their natural lengths and time scales. So we have time resolutions in the order of a few seconds that started back in 2011. At the time, that was the first dynamic experiment where you didn't have to stop to take an image. We simply continued flowing at otherwise unchanged conditions. So we maintained the visco-capillary balance, just kept injecting. And at the time, the high-speed cameras worked with internal memory. You could record enough projections for like 7 scans, which has then tremendously improved with continuous readout interfaces where you can just scan continuously. There was a bit of a drawback on the time resolution in 2012, but by now that is continuous readout at 1 second time resolution. There are various synchrotrons in the world that can do that. We have very good experience with the Paul Scherrer Institute, the Tomcat beamline at the Swiss Light Source, but there are many other locations and also new locations like in Brazil that are focusing on this topic. So this becomes more and more accessible. So apart from very nice, colorful images, what have we learned? Well, there is actually things that people in the traditional flow experiments have never really bothered about so much. So when you do a flow experiment, this is a traditional special core analysis experiment where we take a 5 centimeter large rock sample saturated with oil and water, and we inject both simultaneously in a so-called fractional flow experiment, and the purpose is to measure relative permeability as a function of saturation. And I'm showing you here on the left-hand side the raw data from such an experiment. For instance, in red, I have the pressure drop. In orange, I have the saturation. And the fractional flow is changed from 100% water to 100% oil. So that is the clear step curve. Yeah, so the fractional flow is imposed, saturation follows, and simultaneously we measure pressure drop, saturation with in situ X-ray measurements, but also resistivity, for instance. And we see that intermediate fractional flows, so intermediate saturations, we observe. So the saturation range would be roughly between, let's say, 80%, let's say something like 80%, 70%, and something like, what is the fraction flow here? 50%. we see a lot of fluctuations in almost all measured quantities. And that has traditionally never been considered for anything. So in the analysis of such experiments for computing capillary pressure and relative permeability, all these plateaus were simply averaged out and an average value was taken. But the fluctuations were never really been considered and sometimes even considered as a failed experiment. But when looking at the same situation in a microcity flow experiment at the synchrotron beamline, we actually see what is happening at the pore scale, and that saturation and pore scale fluid distribution is not constant. And we were lucky to capture one of these events back in an experiment in 2013, I believe, where we saw an event of similar magnitude in terms of pressure signature and also saturation signature, where we clearly see the saturation distribution changing at the pore scale, changing back and forth actually. Some groups call that intermittency. Intermittency means that there is transport without permanent connectivity. And we indeed see also in this, we also see in this experiment, when we look at the relative permeability that we calculate from that particular data set, we see that in that event, the connectivity is indeed changing. So this is a connected pathway flow connectivity, relative permeability, and the connectivity is changing in this event. So there is clearly a change in fluid topology at the pore scale. Now, having noticed this, we went back to even older data sets, which is a data set from 2012. And we noticed, when you look very carefully, so this is a drainage experiment where an oil phase in green is doing forced primary drainage into a sintered glass material. And you see that in the beginning, that cluster at the bottom is growing without permanent connectivity to the top. So the injection is top to bottom here. And we removed the rest, so the water phase is gone. So you see here, the oil cluster is growing, but you can't see a permanent connectivity. And the question is a little bit why this is happening. But first, just to complete the phenomenology of that description, that is actually much older. In the late 80s, people like Herb Yuan have already done experiments of constant rate, rate controlled mercury intrusion. Yeah? So the rate is held constant. That is different from a mercury intrusion experiment as it's conducted to measure pore size distribution or so, because these are pressure controlled. So if you conduct a rate controlled mercury intrusion experiment, you already see these zigzag type of curves. So in Apologies, in their publication, they inject here from the right to the left, because that is how mercury experiments are typically plotted. When you compare that to the pressure signature in our experiment, which is now plotted from the left to the right, you also see the zigzag curves. And we have in addition images from the pore scale where we can clearly see what has happened in the meantime. So we can see these events. And what's happening essentially is that a meniscus is at constant injection rate in this experiment. So we control the rate, we hold the rate as constant as possible. We charge menisci until they overcome a capillary entry pressure, which is here the situation A in the cartoon from Herb Yuan. Then very quickly, we fill a pore. And while that happens, the meniscus is increasing. Also the curvature, the radius of curvature is increasing, the curvature is decreasing. And as a consequence, the capillary pressure is decreasing until the fluids come to rest and reach the configuration in B. And in the configuration in B, you have again a meniscus, but that has typically a lower curvature and therefore a lower capillary pressure. And this is why the bottom pressure of this event is lower than before. And then we keep injecting at constant rate, we recharge the menisci, and the whole procedure starts from the beginning. So we looked at our data sets and we see a lot of these zigzag curves. And in particular in primary drainage, we see that some of these filling events are not just individual pores like in the cartoon of Herb Yuan, but they are filling multiple pores in one go. And they can be as many as 10 pores in one step. So that is something that at the time we were like looking for what is now different that we can image that's different from the description in the literature. And it's not, I would say, dramatically surprising that this happens, because also percolation models would expect that you fill multiple pores in one go, potentially. but the difference here is simply that in the dynamics, if you have a very narrow pore throat, which is the initial barrier, and after that you have pore throats which are much bigger, your meniscus can advance through that whole pore space in one go, and it's not really held up. And that's the consequence of the dynamic of these filling events. Now the question is, what does this mean in terms of energy dissipation? Of course, when you look even in the very old papers from Norman Morrow, that the capillary pressure curve has, as a matter of fact, these rheons and isons, which I just talked about in the previous slides. And that leads to energy dissipation. And in normal special core analysis, we never really notice any of that, because we measure individual points. So we measure basically the top points of that curve, and we fit a smooth curve to it, and we don't take these rheon isons in the capillary pressure curve into account. And in the relative permeability measurements, we also average over the plateaus. So it's not really part of our mass and momentum balance in that sense. It is only an average mass and momentum balance, and the respective energy dissipation is not taken into account at all. So we were wondering how much energy is actually getting dissipated. So James McClure started developing a more rigorous formalism to that, where we look at the rate of internal energy dissipation, and there depending, and the important part is that these are space and time averages. And here we can then group different contributions in different ways, and we can identify, for instance, these isons and these rheons. Yeah, and some use the average pressure, and the other ones use dedicated, specifically the pressure fluctuations. Okay, so here is a very simple analogy, and I would be really interested in your perspective on that, because when I remember for my graduate school classes, the fluctuation dissipation theorem, which is typically used for thermal systems, for thermalized systems, where the energy scale, the scale of the energy scale of the fluctuations is a thermal energy scale. And in our case, our energy scale is much higher. It's a capillary energy scale. And this is also why, in particular, your group has created the term non-thermal fluctuations. So if you look for non-thermal fluctuations, you find your paper actually, or Alex Hansen's paper. And the question is now, can we apply the fluctuation dissipation theorem? So I just regrouped that a little bit. So we have here, so the fluctuation dissipation theorem basically says that in linear response systems, we can relate the structure factor to the imaginary part of the susceptibility. And the imaginary part of the susceptibility is basically the rate of dissipation term. And we could relate that to the term that James McClure was derived. And then I basically move the frequency to the other side. And in a very intuitive way, it basically simply means the rate of dissipation is basically the dissipation of fluctuation times the frequency times the spectrum of the fluctuations. This is a very hand-waving way, and I realized that, and now we need, in order to test that, we need some ideas about what is the spectrum of the fluctuations, where we can get that, for instance, from event size distributions. So how many pores do we fill in essentially one event? Only you would need to translate that into the frequency picture, which we haven't really done yet. Then we would need to know the frequency of fluctuations. How often do they actually occur? At which rate in time? We have some histograms of that, how many per minute, from unfortunately a different experiment, so we can't put that together. So this is a very conceptual figure. And we need to know what is the dissipation per fluctuation. So I'm going to focus on this dissipation per fluctuation now. And I showed you these figures already before. So we have the zigzag curves in the pressure time or pressure injected volume plot. And the logic from that old work from Herb Ioannis, you charge your meniscus, the pressure is increasing. This is reversible up to the instability point where the Haynes jumps happen. Then you have the jump itself and you jump down. This is where your pressure drops rapidly because you convert some of this capillary energy into kinetic energy. You accelerate the liquid-liquid interface. So there's mass in motion. It gets dissipated and it comes to rest at a new curvature and new interface. So there's the interfacial energy has probably changed, and some energy has been dissipated. So we don't know exactly how much, but we can estimate that by saying, yeah, you keep injecting at constant rate, and the amount of dissipation that has occurred is maybe related to the amount of work that is required to reach approximately the same pressure, the same capillary pressure in the system as before. And then there is a reversible part. So this is also reversible, but the reversible part is used as the measure. Yeah, so the sub-ison is used as a measure of how much has been dissipated. And if you look at the ratio of these two and integrate it over the whole curve, you see that the sub-isons is actually about 60% compared. So the dissipation is about 60% of the total energy. And that is in the same, I would say, ballpark as some much older work from Norman Morrow. It goes back to his paper in the 1970s, which had a more recent pickup in 2007, where he calculated this efficiency of drainage, ED, which is simply how much of the pressure volume work that is going into capillary energy is translated into new surface energy. And for a particular case, for one pore filling event, I don't have that on my slide now, we confirmed that one-to-one, because you need to measure the new interface, and then you need to interfacial area, you need to estimate the interfacial tension, and then you can estimate that. But the interesting thing is that you have, depending on the pore space morphology and topology, a varying degree of reversibility. For sphere packs, you're in the 80 to 90% range, but for sandstones, in particular limestones, you can be as low as 10 to 20%, which means that most of your invested energy is dissipated. Now I wanted to make an estimate how relevant that really is and how much our two-phase Darcy picture is really wrong. So I make a hypothetical comparison, and I compare the energy dissipation in all of these events to a hypothetical situation of connected pathway flow where I use two-phase Darcy. So I just, this is two-phase Darcy. I just rearrange it, and then I use the pressure as for the pressure volume work term, and I calculate that, and I get a certain amount of energy, and then I calculate the dissipation in all of these events. And when I take the ratio, I find that this is basically a factor of 200 underestimated. The connected pathway flow underestimates the energy dissipation in this situation by a factor 200. Okay, there are some issues in my calculation. I don't account for the surface energy in all of these events, but I know from the previous slide that this is a kind of a factor 2 uncertainty. So I'm still missing a factor of 100. So if you take this literal from this simple calculation, it would basically mean that in primary drainage, that's the situation we do in CO2 sequestration, we are underestimating in the two-phase Darcy approach the energy dissipation by a factor of 100. And that makes a big difference. So I'm not saying that this is ultimately true. I'm clearly warning this is my back on the envelope calculation. And it is more like the call for action to look into this in more detail and do it properly. And James is exactly starting to do that. So I gave him my data set from our beamline experiment, and he looks at the pressure volume curve. And now there are two different ways of dealing with that. You can basically decompose it in these risons and sub-isons as I did, and then you get a very strange histogram of events. It's very non-symmetric. And James did it differently. He basically uses a moving average window approach, and then he approximates like a smooth curve and calculates the difference to that smooth curve. And from that, he gets the fluctuation on top of the smooth, sort of slowly varying curve. And when you look at then the spectrum, the histogram, it looks much more symmetric. There are still non-symmetric parts in it. And at the moment, we are investigating how that skewness of that distribution depends on the averaging window size and things like that. Then he is developing a very rigorous formalism looking into the entropy generation rate, which is linked to the change in the dissipation rate, obviously, and decomposing that into the classical terms, which is like work of Darcy flow, but then also pressure volume work, fast fluctuations, slow fluctuations, and curvature constraints. So I'm coming to the whole curvature story a little bit later. So that is where we stand right now. This is very much work in progress. I just wanted to give you like a look ahead. Yeah, so this is like a sneak preview what we are working at right now. So this is last word is not spoken. In particular, we want to make quantitative assessments of how big these terms are. And depending on exactly how you look at it, you still see that some of the fluctuation terms make contributions like in the 10 to 20% range. We haven't really seen the factor of 100 issue yet back. And there could be various reasons. But ultimately, you have to do things very carefully. In my back on the envelope calculation might exaggerate the situation a bit. But this is now going in a more rigorous way. Okay, so having talked about dissipation, the root cause are these pore scale events. Drainage events and Haines jumps are particularly dissipative. In another series of experiments, we looked into imbibition, and we noticed that oil clusters break apart, oil phases break apart into clusters. So we have here in red the total oil, and then we decompose it into red color and yellow color, where red means the oil is connected and yellow means it's disconnected oil. And over the imbibition experiment, we see that the fraction of disconnected oil is really increasing, which makes sense. And we capture then from our time-resolved tomography the connectivity and can then identify by difference images where snap-off events have happened that disconnect oil. And you see such a snap-off event here on the right-hand side. Yeah, so there are narrow pore throats where the oil phase in red is disconnected, and then you get sometimes isolated oil clusters. And that is also reflected in the Euler characteristic, because the Euler characteristic is very negative, which means an overall degree of connectedness in the beginning, which is then becoming more and more sort of closer to zero. But the really interesting thing is, and that is because we have snap-off events. So we see the snap-off frequency at some point is really dramatically increasing. And I can explain to you in a second why that seems to happen in such a sort of coordinated fashion. Because these snap-off events, they do occur all the time, but they don't lead to complete disconnection. Because ultimately, you can lose, let's say, this is what the Euler characteristic means, but I guess you're familiar with that topological measure. It basically means how often do I have to cut an object that has multiple connections in order to become really two objects. And that seems to happen here in the beginning, but we are not really creating separate objects, meaning that the oil phase is still connected via an alternative route. Only at some point, you really disconnect the oil phase. And exactly in that moment, you also see coalescence events. That was a bit surprising, but when we looked at the pore scale in detail, we saw that the disconnection of one leads to the connection somewhere else. And that simply happens because when you disconnect it, you change the capillary configuration and you release some of the capillary stored energy that forms a capillary wave and a pressure pulse that can make menisci oscillate. And when you look at, for instance, at micromodel experiments with high-speed cameras, you see that the menisci really oscillate. And that can connect to an adjacent pore. And then you have changed your connectivity. And as a consequence, you have effective mass transport without a permanent connectivity. So for the water wet situations, that didn't seem to make a big contribution to the flux. Yeah, James McClure has calculated that in a simulation study, except when you're very close to the residual oil saturation, you don't have that much flux contribution, but you have a very big contribution in changing the topology of the connected pathway. So it does make a big impact on the transport. In mixed wet situations, that's different. So the same occurs in principle, only at a different time scale. It's much slower. And the video here on the right-hand side is in a mixed wet situation. It's also a different geometry. But yeah, I have to point you to the paper, the 2019 GRL paper. There is a water wet data set for the same rock, and we see the same phenomenon as in the sandstone rock above. When you change the wetting properties, the dynamics becomes a lot slower. It also seems that these pressure fluctuations that I showed you in that special core analysis experiment, you don't see that as much for the mixed wet experiments. But it doesn't mean they're not there. They're actually a lot more. It only means that their pressure signature is less. And this is why people, they are not there. But when you look at it, there's a lot more. They seem to be slower. Oil menisci move back and forth. And the overall flow regime is more like a superposition of connected pathway flow and ganglion dynamics, whereas in the water wet situation, you have more like a decomposition, a time decomposition into long periods of connected pathway flow only, and then very, very brief periods where pore scale displacement events happen. In mixed wet situations, that seems to be much more superimposed, and also the ganglia transport flux. Now, Ryan Armstrong has done an independent study where you could directly see how much flux contribution is there, and it is significant and it cannot be ignored. So I mentioned already to you that the significance already in the water wet situation is that these events change the connected pathway. And by doing fractional flow experiments, so this is now a different experiment, but the same phenomenon, we are co-injecting water and oil in different ratios. So in the same way as that relative permeability steady state experiment I showed you in the beginning, but now at the pore scale. And we noticed that in all the experiments where you had the direction towards a non-wetting phase saturation increase, so I plot here oil saturation, I plot the Euler characteristic versus the oil saturation. When the oil saturation is increasing, this has character of drainage. All the data points lie on one bounding curve, which happens here to have a very specific exponent. But when you look at that paper from Steffen Schlüter, the exponent depends on the rock type and in other things. But the important part is that all the imbibition experiments, they lie on a different loop. And we can also explain why, because in drainage, we maintain connectivity and avoid forming loops. And in imbibition, we have snap off and we form clusters and we maintain the loops. And that is ultimately the reason why hysteresis happens. But the real significance of that experiment, this was the moment when we realized that in order to describe the state variables of capillarity, the reason why hysteresis exists, or why it's perceived at least, is that the Euler characteristic needs to be considered as well as a state variable because it is also hysteretic. That was the idea. And I knew from the group of Casey Miller, Bill Gray, and James McClure that they tried to close the capillary pressure hysteresis by considering a capillary pressure saturation and interfacial area, and that it did not fully close. And then I thought, yeah, maybe there's another property which is hysteretic. If you put them all together in the right way, they might eliminate the hysteresis completely. And that turned out to be actually correct. So in a nutshell, how should we look at it? So our Darcy scale, macro scale saturation functions are in principle a function of the pore scale fluid distribution. Yeah, so what we see in our capillary pressure curve is always a function of the pore scale fluid distribution, and that is process dependent. That can always be different depending on whether you make drainage, imbibition, or on a scanning curve, and that we know from the figure on the right hand side. But pore scale fluid distributions are just geometric shapes, geometry in 3D. And the question about the state variables only boils down to the question, what do we need to describe these shapes in 3D? And there's an answer to that question, because Hadwiger's theorem states that any linear additive property in 3D can be uniquely parameterized by four Minkowski functionals. So at least for capillarity, that is probably the answer. And just as an analogy, if we take, for instance, the ideal gas equation and don't use all of the state variables, we inherit a apparently hysteretic behavior. For instance, if you ignore temperature and only look at the pressure volume plane and do Carnot cycle, we have something that looks like a hysteresis loop. But of course, the ideal gas equation is not hysteretic because it's just a cut through the parameter space. And our hypothesis was that exactly the same thing happens when we look at capillarity. Yeah, and then James was, so these are the four Minkowski functionals. They are volume, interfacial area, then the mean curvature. So it's actually the area integral over the mean curvature. So it's the mean curvature, but in capillary equilibrium, you would assume that the mean curvature is constant. So that translates really to just the mean curvature. And the integral over the Gaussian curvature, which is related to 2 pi times the Euler characteristic. So James was running 260,000 lattice Boltzmann simulations, or at least computed 260,000 different fluid configurations for 6 different rocks. And then he created a response surface for all the different capillary states and tried to parameterize them either with saturation only, saturation interfacial area, and Euler characteristic. And then he calculated the least square error between each individual point and that fitted response surface. And you clearly see that if you only consider saturation, then the error is very large, meaning that the response surface is not a very good description for all data points. And then the error decreases the more parameters you use. And for the using all four Minkowski functionals, in the end, the error is on the same order of magnitude as the experimental error. And that is about the same level of accuracy at which we have a validation for the lattice Boltzmann simulations. So within the typical range of uncertainty that we have, that leads now to, I would say, to closure of the system for capillarity. For dynamic properties, that might be still different. Okay, so there is a little bit of progress on that. The four Minkowski functions are not linearly independent. And maybe I should start differently. So when I showed this for the first time to Majid Hassanizadeh, he was not particularly happy. And he said, yeah, but then you need an evolution equation for the Euler characteristic. Okay, there is a little bit of an answer to that now. When you look at the most recent paper, the four Minkowski functionals are not independent. And you can make like a dimensional analysis and arrive with 3-dimensional groups. And you can now basically formulate the problem by saying we are looking for a hypersurface, which is the relationship between these 3-dimensional groups. So a hypersurface where a function of these are 0, or where 1 is the function of the 2 other ones. And that is plotted here on the right-hand side. These are lattice Boltzmann simulation results for a range of different geometries. And then we can fit a response surface to all of that and use that to predict the drainage inhibition cycle, the Euler characteristic for drainage inhibition cycles for a specific rock that is part of this family. And indeed, it seems we can kind of predict that. Last word on that topic is probably not spoken yet. Okay, just to summarize this part, it seems that we found, at least for quasi-static properties, a way to go from the Pore to the Darcy scale. There is a scale in between, which is the cluster scale. We have interaction between these clusters. There are Pore scale displacement events and associated physics that changes the topology. We need to describe that. The Minkowski functionals are an adequate way to do that. And this way we arrive at the Darcy scale for quasi-static properties. dynamic properties we are working at right now, the axis is via, the first we need to really solve is what happens to these fluctuations, because that determines the rate of entropy generation, and that needs to be looked at. But there is something else that we noticed. So when we go to mixed wet systems, it's not only that the flow regime changes, but we also noticed that the system that forms more like sort of biconvex terminal menisci fluid configuration in the pore space in water wet systems, which is very nicely described by mean curvature, goes to an almost zero mean curvature situation in mixed wet systems. And when we looked in detail, it turns out that these come along with negative Gaussian curvature. So it basically means that one radius of curvature is positive, the other one is negative. They have similar magnitude, and then the mean curvature, they cancel each other in the mean curvature. But it doesn't mean that the interfaces are flat. They have just bicontinuous form, which means that also there is a simultaneous connectivity of two fluid phases. And it could be that this is favorable actually for transport, because you avoid these dissipative pore scale events. And the respective relative permeability is much more favorable than the purely water wet situation. Yeah, so you of course decrease a little bit some of it, of the oil relative permeability, but you reach much higher, much higher water saturations, so much lower oil saturations, and maintain an overall still acceptable relative permeability for the oil phase. So this is interesting. Also, it makes a difference if you look at the connected and the disconnected part, because it seems that the disconnected oil doesn't do that. It doesn't form these bicontinuous interfaces. It's mainly the connected part. So in some sense, we are looking at a situation where we form minimal surfaces inside of a geometric constraint. So if without constraint, it's a sphere. Inside of a geometric constraint, it could be a different complex structure, but overall still with like sort of biconvex terminal end caps, so like a sphere end cap approximation. But if you also expose this to flux boundary conditions, then it seems we are favoring these bicontinuous structures. And it could be that there's an underlying principle that the system is trying to minimize its rate of dissipation. That's more like an intuition. I'm not sure if it's really true, but that might be a leading idea to investigate whether this is really true, because it could be a universal phenomenon. The other aspect is that I actually lied to you that the Gaussian curvature is related to the Euler characteristic by a simple equation. The equation is more complicated. And that has to do with the fact that only in closed manifolds, the integral over the Gaussian curvature is 2 pi times the Euler characteristic. And then we have, for instance, a sessile droplet in mixed wetting conditions. We have partial wetting. We have an intersection with another solid. And we don't have a closed manifold anymore, which means that in our integral over the Gaussian curvature, we can't execute that integral over the whole surface anymore. Part of it is missing. And that is captured by this geodesic curvature term. Yeah, so this geodesic curvature is for like a spherical droplet on a surface. The contact plane is a circle, and the geodesic curvature is the radius of curvature of this circle. And our idea was to simply say, well, what if this, it basically means that there is a part of the first integral which is just lumped into the second one. What if you lump it instead in the contact angle and say this is actually the contact angle? It turns out that this is actually working out. So you have to do a little bit of derivation, and I really don't want to go into detail in these. It's described in detail in 3 papers mentioned here. 2 Journal of Colloidal Interface Science papers, 1 geophysical research letter. So the idea is the geodesic curvature is actually along the contact line is lumped into a deficit curvature. It means simply it's deficit curvature of the first integral, and that can be translated into a macroscopic contact angle. So we can calculate that, and for a spherical droplet, we can derive a analytical solution, and it relates the macroscopically observed contact angle to this expression. And interestingly, it's not one-to-one related to the intrinsic contact angle. This is the one you basically impose from the traditional microscopic wetting situation. And simple evolutions with surface evolver are confirming that this is indeed what you would get. So this is what you would observe. It still looks a little bit strange and it didn't convince me entirely. Why wouldn't you get a one-to-one line? But then we found this old data set, which is also from Norman Morrow. He plotted here the advancing and the receding contact angle as a function of the intrinsic contact angle for different material combinations. And he made the surfaces rougher and rougher and rougher, and observed that at some point, the advancing contact angle doesn't increase anymore and the receding contact angle doesn't decrease anymore and forms bounding loops. If you now take the average, because let's say if you have a droplet sitting on a surface and you move that droplet in one direction, you have the front advancing and the back receding. And our integral geometry approach at the moment doesn't make a difference. We'd have to take the average. And if you take the average, then we find that our spherical approximation superimposes quite nicely with the average of the advancing and the receding from the Norman Morrow data set. Because when you look very carefully, it also has this S-shaped character. Only at the ends, Morrow kind of put a line to it. And you could argue that this line, when you look on the original data set, it would be, as a matter of fact, more like a smooth transition to zero. And if you do that, then it would be almost a one-to-one fit. So that convinced us quite a bit that we are up to something that might be of more universal character. How does it work out in practice? We can also compare that to purely geometric contact angle measurements, for instance, from the Imperial College group inside of the pore space of porous rock. And it turns out that it's not working out too bad. In particular, when you compare systematically the different approaches that there are, it seems that some of the geometric contact angle measurement approaches have quite a bit of a bias at the ends, whereas the integral geometry approach has a much more natural way of representing that S-curve. So it seems that some of the approaches that work on geometric basis have, because of a lot of experimental reasons, a bias. And might not be that reliable. It seems that the integral geometry approaches have a bit of an advantage here. Before I close, I want to mention that if you assume reversible thermodynamics, so you put your droplet, so it now means contact angle per se is not a thermodynamic concept. It's just geometry. But if you want to relate contact angle to interfacial energies, this is where thermodynamics comes into play. And we can indeed derive Young's equation by assuming reversible thermodynamics. And also, apologies here, this is really very much shortened. So we apply reversible thermodynamics where we have the second law, we assume flat solid surfaces. And for a spherical cap, you get in the end Young's equation. These derivations are shown in the paper above. Now, the latest is, and that we haven't shown yet in the paper, that is also in progress. You can apply the same methodology to derive the Wenzel model and the Cassie-Baxter model. So it seems that by separating the geometric nature of wetting and the thermodynamic aspects, we come to a very consistent description of wetting, which might be a lot more universal than what has been used so far, because you can use it to describe systems over a wide range of surface energy ratios, because they also might end up in complex geometric states, like this Cassie-Wenzel-Baxter, but also topologically varying interfaces and surfaces, where in the end, the state of the fluid is complex. It's a complex geometry, and the approach using integral geometry might be much more universal. You can also describe topological transitions and bicontinuous structures, which we have already demonstrated in that one case from that work from Imperial College that Louis Lin was discovered. So perhaps this is heading to a much more universal description of wetting, and that is more like a question to the surface science community, whether they find that useful. Okay, with that, I would really like to close and not forget to mention all the people who contributed. It's really a lot of people present and former colleagues at Shell. So you notice Ryan Armstrong was a postdoc at Shell. In the meantime, he has his own group and his own PhD students. We still collaborate. People from the University of Mainz, who in the meantime also moved on, and Maya Rücker just became assistant professor in Eindhoven University. Collaborators from many different places, Rudolf Hilfer, Steffen Schlüter, I should not forget, who was then a postdoc with Dörte Wildenschild, and and lately also the Imperial College Group is jumping on that quite a bit. So there's a lot of contributions from many people, and it's the only way of actually making significant progress. Without the modeling capability from James, we would have not been able to test these things so well. And this is why it was quite key to collaborate with so many different people. Okay, and with that, I really would like to close.
Thank you so much, Dr. Berg. It was so interesting question.
Well, thank you very much for your very immensely, I would say, rich talk. It's you make it very hard to start questioning here. So, but let me just say first that I really like your explanation of the source of hysteresis, and the answer to the question, can the fluctuation dissipation theorem be applied? I think is yes, but you have to define the fluctuating variables may be different, and maybe that also relates to my question really, because if we look at the time rate of change of entropy that you had at some point, you expressed it with the work of Darcy and with the PV work. Yeah, this one. But I don't understand the last terms, because here clearly you are trying to combine the Gibbs equation the way I see it then, and I'm asking you to confirm that, and then you do it in the way we normally do in irreversible thermodynamics. You introduce the energy balance and the momentum balance, but then all the rest is in my mind not there. Where did that come? Is it a plus, or should I not? The three bottom lines, are they connected to the two top lines?
Yes, they are. And we start really from the Pore scale. And this is a consequence from a time and space average of these. And I think in a lot of approaches, these terms would have been averaged out, basically, because the assumption is that in RAV scale, these terms should have averaged out. And that's a bit the discussion. So, okay, to begin with, the last word on this is not spoken. So this is very much work in progress. And the discussion we have at the moment is that the argument is that at the RAV scale, it should have averaged out, and these other terms would simply disappear.
Okay, that I understand.
But we are not fully convinced of that, because
let me ask a key question in that context, which I have been wondering about many times. If you have a porous media filled with something, and the composition in one end is different from in the other end. Now, consider it at isobaric conditions. Will you then have any flow?
Okay, I think there are two things that I think that was also one of the questions that I always was asking myself in the Hassanizadeh and Gray theory. Whether that really, if you have a gradient, whether that can lead to flow. But that I think that depends on how that gradient compares to the energy barriers in your system. Because we think ultimately this leads to like a rugged energy landscape. And then is the question, is your driving force bigger than these energy barriers, like the local energy barriers, or not?
Okay.
That I don't know. It's not so easy to answer. So I would love to basically calculate or have an idea about how big these energy barriers are. And the complication, and yeah, so apologies, I'm just copy pasting something from a paper here in the background that you can see it all. So this is from a paper where we calculated in a simple, or maybe I should copy paste something else. So we how do we do this? Okay. So we have this is from a micro model experiment. It's a very simple geometry. It's a hexagonal geometry. And we have imaged with a high-speed camera pore scale displacement events. And we wanted to estimate, indeed, what is the energy landscape. So we wanted to know what are the different distributions, but also what is like inertial, what are the inertial forces, what are the viscous forces. And it turns out that each displacement event has a certain zone of influence. So we had a big difficulty of doing that estimate because we didn't know in the end how much mass is in motion. Because in these experiments, we didn't really image the flow fields. Okay, we could have, but these events are so fast that it's difficult to do particle image velocimetry. But then we gave it to, at the time, our collaboration partners from Schlumberger, who have a similar type of simulator, maybe even more sophisticated because it's a free energy-based approach. And we asked them, can you calculate us the flow fields that are associated with these displacement events? And we noticed that these displacement events have a certain range, and that at each little peak that corresponds to a pore throat, because this is where the flow velocity is increasing. So you have like a Haynes jump, and that is driving a flow field that ranges over, in this case, 1, 2, 3, maybe 4 pores. And my argument why I'm not convinced that the REV scale, this is averaging out, is simply that for averaging out, you would have to have a larger averaging volume, but the range of these displacement events is very finite. So it could be that they actually have they are not really seeing the REV anymore. So there is so you could define an REV as the length scale over which these other terms have averaged out, right? So,
yeah.
If these events don't have the range to actually do that? That is something we don't know.
Yeah. Okay. Thank you.
But I mean, you're spot on with your question, because that is what I have my debate with James.
Yeah, we have to define our REV properly.
Yeah, indeed. And you could indeed. But then it's a matter of the pore scale dynamics. So in some sense, we are choosing here a bottom-up route where we don't prescribe yet a priori that they do average out. We simply want to see that this happens. And that is what the equation captures. Because there could be also effects in films. You see here the pi, which is the disjoining pressure. And you also see the geometric constraints that come out of the geometric evolution of the curvature, because that imposes a constraint on the possible evolution of the system. So that is related to basically this slide here. So these terms show up because you need to have independent measures to construct a thermodynamic potential function. They need to be independent of each other. And that is where this paper fits into the roadmap of the work. Yeah, James looks at this much more as a theoretician, yeah? And he says, okay, before I can do thermodynamics, I need like the geometric constraint articulated in a linearly independent way. And that has been basically done here. Just maybe as explanation.
Thank you. Any other question? Any other question from the online participants? If you have any question, just raise your hand or unmute yourself.
I have a question, Steffen. This is Carl Fredrik from Trondheim.
Hi, Carl Fredrik.
On the last part, where you were calculating the contact angles with the Gauss-Bonnet, you sort of drew a parallel to the work on Morrow, where you had advancing and receding angles. I didn't really capture how you did that jump, because your calculations, they are done on pure, I mean, they are just mathematical flat surfaces, right? Without any roughness or...
No, these are done in porous. Yeah, these are rough surfaces, but they have also complex topology, right?
Yeah, but those are the actual experimental results. But you compare those.
But they are basically they are sessile droplet experiments. Basically, this is why I think that the situation in principle, the equation of a sessile droplet should, in principle, yeah, I should have said this. Sorry about that.
Oh, okay. So those red balls there are not simulations; they are actual sessile droplets.
Yeah, they're experimental data. They are experimental data.
Okay.
And there are more papers. There is one where he shows exactly which fluid pairs he used and which kind of surface patterning he considered. And then you see a lot of data points inside of the hysteresis loop. So inside the hysteresis loop, everything is possible. Yeah, and it also, in some sense, shows the misery when you do these kind of geometric measurements, because what you measure, when you look very carefully, so we have here, let's take the geometric approach from Matthew Andrew or Alessius Canziani, which is these blue points. Let's say this ranges from 20 to 100 degrees. Yeah, so we can see this here from 20. So like, let's say the difference from hysteresis loop, you would have receding at 20. Yeah, but if I go to 80 degrees intrinsic contact angle, you go here easily from 20 to something like 120. So we have 100-degree wide distribution. So my suspicion is you're measuring actually this whole range, and there should be data points in there, because when you make complex displacements, you measure it after the effect. Yeah, you measure after a lot of different individual displacements. So menisci move forward and backward. So we have any possible combination within that hysteresis loop. So what do we now actually measure? Well, in some sense, I believe we are measuring here the distribution function of the fluctuations and not anything related to wetting. Well, of course, the peak relates to the wetting, but you could ask the question, is contact angle really the best concept of assigning? Because what you want to know is the intrinsic contact angle, not the advancing and receding, to characterize wetting as an input for instance, Pore scale simulation. Is contact angle then in principle the right concept? Because it's hysteretic. I think for us, it's very interesting because we probably have a way, it's kind of the distribution function of your fluctuations.
Okay, thanks, that clarified. Thanks a lot.
Thank you so much.
Well, thanks. Any more questions?
No, I don't think so. So thank you so much for the presentation.
Well, thank you for listening. Thanks for the great discussion.
You're welcome, and have a nice day.
You too. Bye.
Bye.
Bye.